indeed, I do not work for NVIDIA anymore, and so as a caveat, the opinions I'm going to express today do not represent NVIDIA. However, I will talk about NVIDIA technology a lot because I know about it. Also, my opinions do not reflect the views of my current employment situation. The other second caveat I will give is that this is a pretty rambling, incoherent set of slides I'm about to present, and I make no promise that you will understand the point, that there is a point, or that I will have taught you about the thing that I said on the title slide. But hopefully you'll get something out of it anyway. So indeed, I did participate as a student in the first ATPESC. I am definitely in this picture, I'm pretty sure. I don't want to point myself out because I think I look pretty bad in it. But Ray appears to be, oh, is this? I forget how the, oh, yeah, there we go. Yeah, there you go, there you go. That was an interesting event. So this was at the Pheasant Run Resort. I think it was here in St. Charles. I looked this up, and it turns out that this place got burned down to the ground by arsonists.
So there was a major fire, not the whole thing burned down, but a decent segment. It was about 2 months ago, and they just recently found it was 4 kids set a fire and then posted it on Facebook.
But yeah, other than that, it was great. I remember, so there was a golf course next to the resort, like right behind it. I had never been golfing before, and I didn't know the norms about golf. So one thing that I didn't know is that I wasn't supposed to take my morning walk along the pathways along the greens. Apparently the golfers were not happy about that. I was just listening to the podcast, walking around in the morning, and guy comes up to me in a golf cart and says, sir, we're gonna need you to get off the course. And I was like, fine, I'll walk out. And he's like, no, we're gonna need you to get in the cart and get back. So, but yeah, it was a good event. I will say that I was probably in the same situation that most of you were in, which is that this is a lot of content, and a lot of it is gonna be brand new to you. So I think it's okay if you're a little bit overwhelmed right now just by how many new things you've just learned. I was too, I think most people are. And I will say that one of the best ways to take advantage of this time is to just meet the people here and the people who are giving lectures, because these are the people that you're going to be working with for the rest of your career if you stay in HPC. I think Tom Papatheodore gave a talk on Oak Ridge stuff last week, and he's a good friend of mine now. And he's also just I didn't meet him at ATPESC, but I met him at, through community events kind of like this one. And so I think you'll make friends and potentially people who will be your boss someday at these kinds of events. So it's worth meeting people. That's probably even more important than the content that you learned over the long term. So ATPESC, the first one was in 2013. And I just want to talk a little bit about where I was as a person at that time, so you understand why I was kind of dumb. I had done a bachelor's and master's in physics, and I had just started my first year in my PhD program. And I was I assume, in the same boat that most of you are in, which is that you are interested in some domain science thing. You probably like programming, or else you wouldn't spend most of your time doing it. But you're not a computer scientist by trade, most of you, I assume. And so you're learning as you go the things you need to do HPC. And that's why you're here, right? Because you want to kind of systematize your thinking about the field that you're entering. And so I was in that same boat. I had done some programming. I started, my first undergrad thing was in MATLAB, actually. And then my senior project was to take the code I wrote in MATLAB and convert it to Fortran. I don't know why I thought that was a good use of my time, but that's what I did. Of course, I had taken C++ as an undergrad, but I really liked the numerical computing aspect of languages like Fortran more. And in my first year of grad school, I started working on this code Castro, which I still am a developer on today. It's basically a computational fluid dynamics code for astrophysics. And it is built on top of what is now AMRX, which I believe you're learning about tomorrow. And I had a good time, I think. I had a lot of fun in my PhD program doing that. I had to learn a lot about a lot of things I didn't know about to do that. In the summer of 2013, which was the summer after my first year of grad school, I was still kind of a noob, and I just hadn't really done much HPC by that point. I think that pretty much the only science output that I had managed to get was to put my 2 stars on the grid, and that was basically it. I, therefore, at the time, maybe felt a little bit of imposter syndrome. Like, there was a lot of really advanced concepts that were being talked about at ATPESC, and I wasn't sure that I was going to ever master any of this, and maybe I would just continue writing my dinky little terrible C++ code that I was trying to do. So just be aware that, like, for the comment I was making before, it's totally okay if you treat this as an introduction to topics that you will follow up on later, rather than feeling like you have to master everything that you're learning in this incredibly immersive 2 weeks. So along the same lines, my introduction to parallel program was pretty random. I think one of the things that's going to be true for a good chunk of you is that you'll work with established code bases, some of which will have wrappers or existing parallelism that require you not to think too hard about the strategy of what you're doing. And so you may not have to try that hard to just get something going on multiple threads or to get something running on a GPU. And in fact, that's even much more true today than it was when I was in grad school, where you can use something like Cocos, and it requires you not to think that much about how to get started. But at the time, this was about 10 years ago now, things were a little bit different. The Oak Ridge Jaguar system had just been upgraded to the Titan system, which was one of the first big GPU systems. And we had this, our group at Stony Brook were big users of Oak Ridge systems. And so we thought it made sense, given that our time was about to be all converted to this Titan system, to learn how to use GPUs. And so we participated in these hackathon events that NVIDIA partnered with Oak Ridge to do in like 2013, 2014, 2015, I don't remember the exact year. But these hackathon events started. I'm sure some of you have seen these by now. Like, there's a ton of them every year. At the time, I think there was just like one per year. And we went down to Oak Ridge and we started learning about OpenACC. And honestly, I did not have a good time. Frankly, and again, personal opinion, NVIDIA Kepler GPUs are really hard to program if you were a scientist doing real science. I don't know if I was doing real science, but it was just hard. Like, the GPUs were very limited in what you could meaningfully do. And the compiler technology was also not there. I mean, this was in the first iteration of the OpenACC standard, and there was a lot missing compared to what you have now in modern OpenACC or modern, like, OpenMP5. We did come up with a fun logo. We called ourselves Team AstroPug after anagramming Astro GPU. So we found a space dog, and that was our mascot for like the next 10 hackathons. But that was a good takeaway. So that was where I was at, honestly. Like, I didn't really do a lot of GPU or parallel program at all when I was in grad school. Like, I was kind of not that good at it. And when I graduated, I got lucky, or I was planning to go to DOE for like a postdoc position. That was what I was sure I was going to do. And one thing that happened was that I had this random connection where I was, I think, at a conference or something like that, and then this random guy from NVIDIA came and gave a talk at my university at Stony Brook. I wasn't there, but one of my mentors was there, and the guy said he was looking for someone to do a job, and that job was to support the buildup of the 2 new GPU systems that were coming online around this time in 2016 or so, Summit and Sierra. And so I thought that that would be an interesting way for me to work in the HPC community and still be close to DOE that I really appreciated, and so I did that. And this is a photo of the team that put together Sierra. There's fewer people in this picture, so you can probably guess which one I am this time. But yeah, that was a lot of fun to do. And I worked with, like I mentioned, Tom Papatheodore. I don't know if he would be proud to admit this, but for about 9 months, he was my counterpart at Oak Ridge on the NVIDIA side before he went back to working at Oak Ridge. But yeah, I helped the installation and bring up of these new Power 9 V100 systems. And that was a great time. And I will promise that I will stop talking about me and start talking about things that are useful to you in a moment. But I just wanted to set the stage for where I was at and how much I learned by taking this job at NVIDIA that I don't think I would have learned any other way, or probably wouldn't have learned any other way. Okay, so the main thesis I'm going to advance about myself, which I'm pretty sure is true, is that I knew not much at all about how computer hardware worked at the time that I started the job at NVIDIA. And a big part of the reason that I was challenged by OpenACC at the time was that I didn't know how GPUs worked, and so I was kind of in the dark about where these random compiler limitations came from. So here's some things that I probably had no idea what they were in 2016. I didn't really understand what the connection was between C++ or C code and like assembly instructions. I didn't really know what a compiler did to take my really ugly Fortran code and turn it into ugly numerical code. I didn't understand, I think, most modern, or even basic concepts in how CPUs work. So I didn't know what a register was. And I'm telling you this so that you shouldn't be embarrassed, but raise your hand if you don't really know what a register is in a CPU. Be honest. Okay, so probably half of you. That's what I would expect. I also didn't know what a cache was. I mean, I knew what it was. I'd heard the concept, but if somebody asked me to explain how a cache is important for performance or just for how a CPU works, I'm not sure I would have given a coherent answer to that. I didn't really know about how multi-threading worked in hardware. I had this vague concept that you all probably have, which is there's a bunch of cores on the CPU, and maybe a thread maps to a core. But if I were forced to explain in any more detail how that works, I don't think I could have been able to. I'm still not sure I can, but anyway. Another thing that I really didn't know about at all was thinking systematically about how server architectures work, and I think that's a big part of what I learned is the fact that you have multiple components on a motherboard, you have a CPU, you have a GPU, they talk to each other in some way, you might have network cards. If you've ever put together your own desktop computing system, you probably spent a little bit of time thinking about this. But what I found is that even though I could have reasoned my way to a conceptual gap, connection between the time I spent hooking a GPU onto a motherboard in my own desktop and how that relates to HPC, I never tried that. So there wasn't really, there was nothing happening in my head. There was no there. I also didn't know a whole lot about other aspects of HPC, like what a network topology really was or that sort of thing. So I consider myself at this time in my life fairly ignorant and only slightly less ignorant in 2022. So you could characterize my understanding of science like so. And I really hadn't felt a strong incentive to learn more. You all are busy. You're trying to get your science done. You're trying to publish papers. And so it's hard to take time to learn about how these things work, right? Sometimes it's really nice that Cocos exists or that OMP Pragma Parallel exists because you can choose not to spend your time thinking about how that maps to the hardware underneath, so you can spend your time writing science. And if I have one major argument to make for you today, it's I'm not going to say that that's bad, because it's good. It's good that you have a way to just get going on Summit or our frontier. It's a wonderful thing that the community has done, that not everyone has to be a hardware expert in order to get going. The argument I will make, though, is that your ability to use the system particularly effectively will be limited by how much time you spend thinking about really what's going on under the hood. And I will even go further and say you don't have to spend that much time thinking about it. You really need to understand a few service level concepts to get 80% of what's important about being successful on GPUs and on modern server architectures. But if you're where I'm at now in your corresponding career, you're probably at 20%, and you need to be at 80%. And so this is not an attack on you, it's an attack on me more than anything else, but that's where I'm coming from. When I worked at NVIDIA, one of my major jobs was to learn how GPUs work in order to teach people about how GPUs work. Because again, when I started, I didn't really know how much about how GPUs worked. I remember one of my first tasks working with the Livermore team, it was clear that the developer at Livermore knew more about CUDA than I did and was asking me for my opinion on something in CUDA. So that was a pretty good sign that I needed to skill up in my job. So I happen to enjoy teaching somewhat, or at least it's something I don't mind spending time on. And so I really learned quickly that the best way for me to become good at GPUs was to put together training content and then teach people. I suspect that that's true for a lot of people because it really forces you to interrogate what are the gaps in your conceptual knowledge and then fill those, because you don't want to be in a situation where you're giving a talk and then somebody asks you to explain the thing that you just said and you can't because you only have surface level knowledge of it. So I mentored at a bunch of GPU hackathons, and I went to presentations given by people who were more senior than me. I watched how they did it. But eventually I became confident enough to start doing training sessions on my own. And I want to talk about some of the things that I had to learn to teach about, just a few, and then share what insights I learned by learning about them. And so, again, this is a story about me, and that's very selfish of me, but the point is so that you can think about what are the conceptual gaps in your own knowledge that you should think about trying to fill, because you probably have many of the ones that I do. This is a typical slide that I had to show in a talk when like 2017. And this is an image, a marketing presentation of the SM in a V100 GPU. So I don't know how much you all have spent thinking about GPUs, so I will take a little bit of time to explain this slide. A streaming multiprocessor in a GPU is kind of like the analog of a CPU core. It's got a bunch of fundamental units that do certain kinds of math. And so, and I apologize to the camera person because I'm about to walk around, but this here is an SM. And the way that you make a GPU is to take a bunch of these and stamp them together on a chip, basically. So V100 has 80 of these things next to each other, working together to parallelize a problem and solve it. The basic way that a GPU gets faster is not by making these more efficient, it's by adding more of them to a chip. And so the A100 GPU, which is the more modern one that's in Perlmutter, had 108 SMs compared to the 80 in V100. And of course, NVIDIA and other GPU vendors did, over time, make the individual SMs more efficient. But by and large, most of the performance gains come from making the GPU bigger. Now, the reason I say that each of these is like a CPU core, and man, the resolution is kind of bad, isn't it? But each of these little squares is an individual math unit, basically. So this little square here represents the unit on the device which does FP64 math. And basically, the only thing that does is add two FP64 numbers together or multiply them and then add them. Similarly, integer units, 32-bit and 64-bit. And so these are like most analogous to what you think of as an arithmetic logic unit or an FPU on a CPU. It's not really right to think about each one of these individual things as a core. If you do that, you're going to be kind of misled in thinking about how this relates to CPUs. Probably the better analogy is that this is like a vector processing CPU, and that you can just have very wide vectors. Like you can process 32 double precision numbers at a time or something like that. Nevertheless, if you look at NVIDIA's marketing material, it will say that there's like thousands of cores on a GPU, confusing everyone endlessly. And that's just how it is. You just have to have that in mind. Anyway, the bit about cores is not the point of this bit. The point is that there was a lot of stuff on here that I didn't know about. I didn't know what register file meant. I didn't know how warp schedulers worked. I didn't really get what the point of caches was. I definitely didn't know what shared memory is, and I'm still pretty confused about it. So there's just a lot going on here, and I had to learn about this. I even was like confused about kind of basic concepts, like what's the difference, like we talk about how everything is, CPUs are 64-bit CPUs today, right? That's not a surprise to anyone. I'm not sure that I would have given a fully coherent answer to what that meant at the time when I was learning about this. But whereas if you look at this thing and you see the difference where there's some units that handle 64-bit math and some units that handle 32-bit math, it's like obvious to me what those two things are different about, right? And I think similarly, if I had spent literally more than zero time learning about how a CPU works and what the instructions are, it would have been somewhat more obvious to me what it means for an instruction to be a 64-bit instruction versus 32-bit. I just literally never thought about it because I was not not only was I not a computer scientist, I was just kind of doing my astrophysics and learning about what I needed to do as I went. I didn't know what like fuse, multiply, add meant. I'm pretty sure I had heard that term, but I didn't know really what it meant. I was kind of confused about like what vector instructions were. I don't know if I'm making myself look dumb or not, but anyway, this is where I was. I will say, I'm not going to talk about the tensor cores that are on. You can ask me if you want about the tensor cores on this thing. Just a random fun fact from the time is that so V100 was publicly announced in 2017, and actually DOE placed an order for V100s for Summit and Sierra years in advance, right? When you go through a supercomputer procurement, you're planning years in advance because it takes that much time to make sure you have the budget for it, prep the machine room, get people prepared for potentially new programming endeavor, especially when one as big as switching to GPUs. So I don't remember when the contract for Summit and Sierra were signed, but it was like 3 years at least before V100, like the systems actually came online. And it's actually the case that I think maybe everyone at DOE, or at least certainly most people at DOE, learned about tensor cores' existence when the rest of the public did, because it was that well kept of a secret. In fact, it was such a well kept secret, I didn't know about tensor cores until V100 was publicly announced, and I had to give a talk about V100 like a week after it was announced. So I had a lot of learning to do at that time. Okay, so all of that to say that most of these things that I had to learn were not specific to how CPUs work. I was really trying to learn about how GPUs work, and nominally that's the thing that I was learning. But in practice, what I was actually learning is like how processors work. And I think that there's a lot of value in thinking about that. And I still haven't spent any significant amount of time reading about how CPUs actually work. Almost everything that I think that I know about processors today are me inferring, like perhaps extrapolating too far from what I've learned about GPUs. So take that for a grain of salt. So what is my argument? Why do I recommend that you think about this too? Why should you spend more than epsilon time thinking about how processor architectures work? Well, there's a lot of limitations in writing GPU code, which you have probably encountered if you've tried to port any code to GPUs before. The most annoying one surely being that it's hard to get printing debugging information. And there are also potentially more subtle ones as well. But the thing that I want to emphasize is that it's the more subtle ones that in the long run will bite you. So I asked how many of you could identify what a register is. And I am not a computer scientist, so I'm not going to attempt to define it. I'm just going to give a useful definition for the purpose of this talk to avoid liability from people who are smarter than me. I'm going to define a register in this context as the source and destination of mathematical instructions on the GPU, or on any chip, really, but in this case, in the GPU. So what do I mean by that? Let's give an example. I have some arrays, x, y, and z. And I want to set the first element of x equal to y0 times z0. The question is, what are the actual fundamental computer instructions that make that possible? Well, one way that you could imagine breaking it down is you go into main memory, RAM, and you read in the value at location offset 0 with respect to array y, whatever that pointer is. And then you copy it from RAM to a register, because a register is the thing that the actual processor knows how to do something with. You do the same thing with offset 0 from array z, and you store it in another register, R1. I'm just using a typical naming convention where R is a register name and 0 is which index register it is. Then the processor now has all of the components it needs to actually do the fundamental multiplication, multiply R0 by R1, gets a result, and it stores that in register R2 or some other register. And then finally, it takes the result R2 and then stores it in the output X0. The fact that this is true, you could go by without understanding this. Right? You could imagine, as far as I've gone so far, that all the GPU is really doing is reading from memory, streaming the data in, calculating the result on the fly, and then sending it back. Your mental model of how GPUs work does not require registers to exist if this is the kind of calculation that you want to do. But in practice, we usually want to do something a little bit harder than multiply 2 arrays together, like at least multiply 3 arrays together. And so why do I say this? Well, it turns out that processors have a fixed number or a maximum number of registers. They don't have infinite number of registers. On an NVIDIA GPU, the maximum number of registers for all of the recent generations is 32 bits. And so a single double precision number takes 2 registers in order to store it. What does that mean? Somebody tell me what that means. Guess what comes next on my slide, or look at it in Slack and then tell me what it says. What is the consequence, or what is a consequence of having 255 32-bit registers?
Half as much as you think you do?
No, sure, like not the obvious thing. You have 127 registers for double precision numbers. What does that mean? What does that mean for you as a programmer? There are contexts in which it means double precision is less performant than single precision. But let's assume we're doing double precision math. What kind of, I'm trying to lead you to the question I'm trying to ask. What kind of code patterns would you not want to write knowing that this is a fact? Say that again? I don't mean like, we'll get to memory access patterns, but that's not what I'm going after.
Precision? You want your instructions to be in the string size that makes sense. So if you use, 150 numbers, you want to use 150 numbers at a time.
Yes, that's more or less what I'm getting at. So what he was saying is, if you, or what I am going to interpret him saying to make my point, is that if you want to use more than 100 numbers at a time, you're in trouble because you can only store 100 numbers at a time. And so you better chunk your work so that you're not using more than like 100 or so numbers at one time. The way that this actually has an impact for you is that typically when you do something like OMP parallel, or you do like a Cocos parallel 4, each thread is going to be identified with a particular index or grid element or particle or whatever your fundamental unit of compute is, your degree of freedom. And it is very common for you as a programmer to do some calculation to figure out what goes in that zone or that particle. Or you're going to do some physics or some chemistry or some biology, do some calculation and store the result. And so the consequence is that if you need more than 100 numbers, like intermediate variables, to calculate the physics or chemistry or biology that goes into your zone, now you're kind of in trouble because you don't have that many intermediate locations to store in. The GPU is limited in that way. And for most of you, if you were writing like an OMP parallel loop, the way that this would pan out is you're going to have some thread, like variables marked private in directive speak. If you have an intermediate array that has more than 100 variables in it, this starts to seem a little bit suspect. And I'll talk in a second about what that actually implies. But the consequence is, like, I think you're probably going to run into this scenario at some point. You're probably going to write code intentionally or accidentally that has a fair number of intermediate variables in it. And so it's worth understanding this. I can guarantee you that the vast majority of developers that I've worked with at hackathons have run into a problem like this, where for whatever reason, they have some loop in their code where, and so I'm sure you do too, for most of you, that you have some loop in your code where you just have a lot of local memory or thread-private memory in order to calculate a result. Because we're doing interesting science, and interesting science doesn't care about how many registers you have. So the fact that this restriction exists gives us a chance to review our code and think about whether we should be doing things differently. So take a second to read this code segment that I made up, and which doesn't do anything interesting. OK, so the main conceit in this code that I made up to criticize or make a point about is that the construction here is that you are, and sorry again, camera person, you are doing some loop. You have a two-dimensional grid. You're doing some loop over the inner dimension, like the x dimension. You're loading your input data into a temporary 1D array. You're passing it to your do physics function that does the actual calculation, the science calculation you care about. And then you have a separate loop which loops over that row in memory and then stores it. This is different from a potential code where we do zone by zone or index by index calculation of the do physics quantity. So my question is, why would we write code like this? Why would it be that I would have written code like this? Well, one reason, in fact, probably the most common reason, is that your advisor went to grad school in like 1990 and learned that this was the way to write code, and they never grew as a person. Another reason is that there may be like good reasons why it actually was written as a 1D routine, even at the time or now. So a common example of this would be if this is like a stencil calculation where multiple elements nearby in space were grouped together to do a result. So like you're calculating neighboring elements you need multiple elements with respect to any one element to get your answer. And so there's data reuse. And if there's data reuse, then sometimes this essentially acts like a form of cache blocking. This is the bit of code that I am going to talk about now when it comes to parallelism. So just keep that in mind. But I'll put it again on some of it on the next slide. OK, so if we were going to parallelize this code, and let's say we parallelize it over the j dimension, it will run on a GPU. There is no problem with slapping a pragma OMP parallel target teams distribute, you know what I mean, over the j dimension. That's fine. This code will work and it'll run. But it may be very slow. And the reason is that if that n is very large, then, sorry, I'm going to keep flipping back and forth, but the n dimension, or the length of n, controls the length of this temporary local array temp input. And so the amount of temporary local memory you have scales with n. And presumably your point is that you want to solve problems with very large n, whatever n may happen to be. So there aren't going to be enough registers to store all of those arrays temp input or temp output. When that happens, the compiler has no choice. It knows how many registers there are on the GPU, hopefully, and it knows that there's only so many that it can allocate temporary data to. So the result that it has to do is it says, well, I have no more temporary storage space on the chip, on the actual SM, in the case of a GPU. So it has to store the remainder of the data somewhere else. And the somewhere else is either going to be the caches or main memory. The consequence is that by the time, as we go through that array through X, we had to store at least some of the data in main memory and stream through that. And so constantly we're going back to main memory in the calculation of that loop. That one thread is going back to main memory multiple times. Whereas the intent, maybe when writing the code, is that all of the data was there for that thread. It was right there ready to go. That was your intent as the programmer, but that's not what ended up happening. So we might be going back to RAM multiple times for data rather than it being in registers. And the fundamental design principle of a processor is that something like a register or an L1 cache has a lot less memory, total space or capacity, but in return, it's much faster to access. So you're going to substantially slow down your code by doing this register spilling operation. That's the bad part about writing code like this. In order to understand the impact, you do have to think about what the actual numbers are. I told you that it was faster. I didn't say how much faster. And I argue that you really can't understand the impact until you have some sense of what the numbers are. So in my hypothetical GPU, the speed at which you can transfer data between the CPU and the GPU is 10 to 100 gigabytes a second, depending on what technology you use. The bandwidth of RAM to the chip is going to be a few terabytes per second on modern GPUs with high bandwidth memory. Less, of course, for the consumer GPUs that use DDR. The bandwidth from the caches is another factor a few higher relative to DRAM bandwidth. So basically 5 to 10x performance difference between like L1 cache and RAM. So you're talking maybe an order of magnitude difference in how quickly you can access the data between the registers and RAM. And that helps, I think, I hope that helps explain why it's actually pretty disastrous for this register splitting operation to occur. It's the difference between a code that can get most of the sticker number and performance on the GPU and the one that looks pretty bad. And Nsight Compute tells you is like 2% of peak, and then you cry and ask your NVIDIA person for help, and you know. So basically, the more we have to go back, the point is, the more we have to go back to DRAM, the worse the performance gets. So why did I bring that up? Well, I could have just said, as a heuristic, don't have lots of local memory. And you would have believed me, because I spent 5.5 years working in NVIDIA, and everything would have been great. But you would not be like more thoughtful about why that's true, and therefore you would not be able to extrapolate that to other lessons. And so I'm telling you that because that's the same transformation that I went through as a person, where I started with heuristics and thought a little bit, scratched more than the surface on that, and started learning why. I think that it's hard to understand why anything is true about HPC performance if you don't have at least some mental model of what's happening at the hardware level compared to your code. And a corollary of that is that you do have to have some notion of like what the numbers really are, which is something that I really didn't pay attention to when I was a grad student. I didn't care at all what the bandwidth numbers in DRAM were. And you don't have to know off the top of your head that A100 has 1555 gigabytes a second, bandwidth. I remember that because I had to, and I was paid to do it. But you do have to know basic things like whatever that number is, that 1 terabyte a second, it is much faster than PCIe bandwidth. And therefore, if you are constantly going back to the CPU, like you're streaming through your data to get to the CPU because you're running on a problem that doesn't fit within GPU memory, you're going to be in for a world of pain. Another consequence of that is that when I started writing code in OpenACC, again, this was in the before times, I really was frustrated by how many limitations the compiler would enforce upon you. And I have worked with a lot of scientists like you who also get frustrated by the same thing. I have been yelled at hackathons by random limitations in the OpenACC compiler. And I get it. It's frustrating. You just want to get the thing compiling and running. And the compiler literally won't let you. I know it's frustrating. But at the time, I didn't really understand what these limitations, I assumed that these were just, people didn't do enough work fast enough. And therefore, if I just waited longer, OpenACC would evolve to do the things that I wanted to do. And I was partially right about that, but I was mostly, in the fundamental, in the big picture sense, I was really wrong about that. In fact, most of the limitations that exist in OpenACC or OpenMP target are there because of how GPUs are. And if you can't do something that seems like an obvious thing that a compiler should do, consider as your default stance that the reason you can't do it is because you shouldn't do it. That would be very bad for you to be able to do that. And we are protecting you from yourselves. I think that this is fundamentally a constant, and almost all of those, by the way, boil down to this point that I was just making about local memory. The vast majority of restrictions, indirectly or directly, come to that point, that GPUs have limited instruction sets and limited amounts of local memory per thread. Some people I think somebody today referred to this thin thread concept. That's one way of describing it. But no matter how you think about it, that's the point. Threads on a GPU just do a lot less than threads on a CPU. And most of the limitations in some way or another come from that. The other set of limitations that people frequently run into is because there's a lot of threads on a GPU, typically you want to be running hundreds of thousands of threads at a time. Some things that aren't that painful on a few threads on a CPU become really, really painful on a GPU. In particular, one that commonly bites people is dynamic memory allocation. Not only do you have this temporary array, but you called a new to create that temporary array. Or the more common way that it bites people is Fortran programmers, and you know who you are. You do allocate in the middle of your parallel loop, right? You can do that, and depending on implementation, it might not be that painful on a CPU, but it's going to kill you on a GPU. And so in practice, the compiler either might not let you do it, or it'll be extremely painful, and the profile will look terrible, and you will ask whoever the poor person is that inherited my role why it's that bad, and we will have to explain to you this this fact, and you will not like it. So I am saving my successor some time by telling you this now. Okay, what else can we learn from that example? Memory access patterns matter, and this is, I think somebody referred to this already. Let's say we put a OpenACC parallel pragma on this thing. I learned OpenACC first, so I'm going to use that even though I know it's not in favor anymore. Sorry. And so just doing the part of the loop that loads the input data into this temporary array. If we do this in this way, I will just assert as a statement of fact that GPUs only achieve peak throughput when they coalesce memory accesses. And memory coalescence refers to taking a larger number of memory requests and making that a smaller number of memory requests. That's how I'm going to define memory coalescence. So I can give you that heuristic and tell you that it's good for memory accesses to be coalesced, and that the way that you operationalize that in your code is that consecutive threads access consecutive locations in memory. That's the way to achieve memory coalescence. I think it's a little bit better if you understand why that's true. I realize it's 8:15. Am I being entertaining enough that I can go a little bit longer, or do you want me to stop talking? Okay. Okay, so a few things about, and if you leave, I won't be that offended. A few things about how GPUs work. So GPUs work by having parallel threads. And those parallel threads operate in groups of 32 called warps. That's true on NVIDIA GPUs. AMD GPUs is 64 threads. I don't remember how many it is on Intel GPUs. But it's some number that's of order a few tens, right? They operate together in a group. And then you have lots of these warps of threads running together in a GPU to do parallelism. Okay, so that's fact one, threads operate in groups. Fact two is, what is a memory hierarchy? Well, you have a bunch of SMs, streaming multiprocessors, light across the GPU, and those SMs have some resources. They have registers, we've talked about that. Each SM on an NVIDIA GPU has L1 cache, that's its nearest cache to it, as well as shared memory, which we're just not going to talk about. And then device-wide L2 cache, so every SM shares the L2 cache together, and then device-wide DRAM, which is in this picture called global memory. Okay, so think about that memory hierarchy. So what is memory coalescing? Well, imagine that we're going to have I'm showing a hypothetical picture in a second, where memory addresses, which are going to be demarcated in units of bytes, are laid out linearly. So we're just going to pretend there's a line. My question to you is, should it matter whether threads access consecutive locations in memory? The 32 threads in a warp, does it matter if they access 32 consecutive locations in memory? The name RAM, random access memory, kind of seems like it should imply the answer is no, because by construction, random access memory means we can go to any point in memory and get it in about the same time. So why is it that grouping threads together matters? What is this memory coalescing phenomenon? Well, that's where you start getting into concepts like cache lines and the difference between memory requests and transactions. On a modern processor, what typically happens is that, including GPUs, you recognize that if 32 threads are accessing 32 consecutive locations, and let's say they're accessing single precision numbers, that means that they're accessing 128 consecutive bytes. If your hardware memory unit can do transactions of copies of memory in 128 byte increments, then you could do all 32 threads can be serviced by a single memory transaction. You made 32 memory requests. That is, the threads each requested 4 bytes. There were 32 total requests. But a transaction is the fundamental unit of actual memory movement on the chip. And so you could reduce that down to potentially 1 transaction if your hardware can do 128 bytes at a time. Typically, and this is typically this concept of gathering multiple bits of memory and then bringing it down through your caches down to the registers typically refers to the concept of a cache line, where you have some number of bytes that you're getting together. The actual notion of cache line is a little bit more nuanced than that, but I'm being lazy. So the point is we're going to get 128 bytes at a time, bring it down, and then that can be a much more efficient way of doing it. You can imagine, right? You have so many memory bus units on your chip to bring data from RAM to the chip. So if you can make it fewer requests rather than more, you have the likelihood of using your chip more efficiently, getting higher bandwidth. A fun fact about the way NVIDIA GPUs work is that it actually doesn't matter what order the threads are accessing. You could have completely random accesses within that 128 byte section of memory. As long as you are requesting 128 bytes of memory, the GPU can actually figure out, like within the time it takes to get the memory, how to then apportion that back to all of the random threads. So that's one of the reasons why me giving you the naive heuristic, consecutive threads access consecutive memory, is a relatively simplified way of thinking about it and doesn't capture the nuance of what's going on here. It's a little bit better for you to understand what's going on under the hood. That's all I'm going to say about memory, because more would be not very helpful for the purpose of this talk. Okay, this is probably my last real example. I'm going to make up an arbitrary timeline. And Ray, if I'm talking too long, just tell me to stop. This is a hypothetical profile timeline. We have an array, a matrix A. I'm going to call it matrix A, and it's n by n matrix, and n is 15 and 36. I picked that number because it's a convenient number for what I was trying to do. We're going to do 3 operations, and we're going to make like we're going to run our code through a profiler, and it's going to tell us these are the times that it took to do those 3 operations. We copy that matrix A from CPU memory to a corresponding array in GPU memory. We have a second array B, which is the same size as A. It's another square n by n matrix. And we're going to do something with it, which is memory bandwidth bound. So the laziest example I come up with is setting B equal to 2 times A. And then we're going to do a matrix multiplication of A and B to get another square matrix C. I'm pretty sure if I remember matrix multiplication right, it should also be n by n. So my question is, these are the times that I made up for how long it takes to do that sequence of 3 operations. Do those numbers make sense? The question I'm going to ask you is, what information would you need to know whether those make sense? I promise you there's a single set of numbers that you would need to make sense of this. What are they? Clock speed, generalized from this. Right, okay. Flops per second is one way. Which of these 3 timeline figures will that help us answer? The first one? The third one. Yes, the third one, because that's where the actual compute is happening. The other 2 things are memory bandwidth bound operations, copying data. That is controlled by memory bandwidth, a number of bytes per second. The matrix multiplication, if n is particularly big, should be controlled by the FOPS, the arithmetic throughput of the GPU. Okay, so now that we know that that's the data, here's the data in my hypothetical GPU. So tell me, given these numbers, by the way, when I was writing this, I thought I was going to be like 25 minutes in, so sorry. Maybe I should just stop. But here's the data. Tell me whether these 3 numbers make sense. Let's go through them one by one. Does the first one make sense? By the way, if you're trying to do this in your head and not using like maybe a calculator, that would be a way to make it easier for you. It's too short. Oh, tell me what it should be. That's the main point. That's the hard part of this question. Oh, yeah, that's an important question. It's double precision. I'm pretty sure that's what I thought. Well, okay, but that's a good. We're going to claim it's double precision for the purpose of this exercise. That is my assertion by fiat. Does anybody want to tell me how long it should take if it's double precision? Does anybody know what the bandwidth of PCIe generation 3 is? Sure, 16 gigabytes per second. Let's call it 10, because A, that's a rounder number, and B, you're going to lose some efficiency anyway. 10 gigabytes a second. So how long should it take to copy A? Somebody walk me through. What's the calculation you would do? What is the size of A in bytes?
1536 squared times 8 bytes.
Right, double precision 8 bytes. So 1536 squared times 8. And then you divide by the bandwidth. That will give you the number of seconds. Okay. How long should it take? 150 milliseconds? Anybody else? That is like bigger than the number that I calculated, so I'm hoping somebody will vindicate my math.
I say I have 1.8.
That's what I've got.
1.9?
Yeah. Like
Milliseconds?
1.88. Yeah.
Okay. Okay, so now you know. That's like a factor of maybe 3x slower than it should be, based on what you think it should be. Now you know that's maybe something I should look into and understand why that's slower than I thought it would be. What about the second one? Same calculation, just with a different bandwidth. Because this is all happening in GPU memory, so it's the GPU DRAM bandwidth that controls it here. That's about right? Okay, good, because I was intending for that one to be right. The last one. Can anybody estimate how many flops you need to do a matrix multiplication given a square matrix n? How does it scale? N cubed, great. So we're just going to assert n cubed flops to do a matrix multiplication. So does this number make sense? Oh, you're saying given 400 milliseconds, it would be 9 teraflops? Yeah, okay. And I said 10 teraflops. So also seems right. I don't remember if that one was supposed to be right or not, but hopefully you see now, right? You take the flops rate, you divide it by you take the number of flops, you divide it by the flops rate, and it gives you how much time it should take. My argument is that you should learn to think this way, right? It's not that hard. It was a very simple exercise. But if you can't think in terms of those basic bandwidth and flops measurements, you won't know whether your profile is just terribly wrong and something really fundamentally wrong is happening. This happens all the time with managed memory on GPUs, where the bandwidth for a copy is way slower than you think it should be, or way slower than it should be, but you don't notice it because you don't know how fast the copy should be. So anyway, rant over. I'm going to skip this. No, I had a funny little thing there. I'm not going to skip that. Use profiling is the main thing that I want to say. You should understand how architectures work, but you should also take the time to profile and then use that profiling exercise to build a mental model of what's going on, and then repeat that over time. So don't regurgitate what somebody else told you about GPUs or any processor, because they probably heard it from the same person who was as wrong as whoever they heard it from. There are some kernels of truth in statements like branch divergence is bad for GPUs. But if you don't profile your code, you really won't know what's going on. Sorry, I'm just deciding whether I had way more here than I thought. And anyway, this meme that I chose is going to be way too old for all of you, probably. You get it? All right. Nope, Chuck Testa. All right. This was way back in the early days of YouTube. Okay, I will proselytize on one more point. Abstraction layers like Cocos make it really easy to write portable code, and they are wonderful for this. I just copied some random code from the Cocos tutorials that just initializes a value to an array to 1. My argument is that you should probably, this is going to get me in trouble, you should probably not use Cocos extensively. No, I don't want to be, that's not fair. Here's what I really want to say. It really benefits you if you know that you can write a CUDA kernel that does the same thing as the Cocos Parallel 4 does. You don't have to write CUDA kernels in your code, because the whole point of Cocos is that this will make you more portable to GPUs other than NVIDIA GPUs, which is now a goal that I feel fine having for you. So I think it's great to use portability abstraction layers. I don't think it's great if you can't even identify what a CUDA kernel looks like and then write the same thing for GPUs, because you don't really know what the abstraction layer is doing. You don't know what kind of code it's generating for you, and you don't really know how to debug it or improve its performance. So the main thing that I'm going to say in this talk, even though I am not chilling NVIDIA in this talk, is that you really should watch the CUDA training series that NVIDIA did for Oak Ridge and NERSC in the last 2 years or so. It's a great series that, well, I participated in it, so I disclosure, I'll put it together. But other than that, it really helps you think, like, get a base understanding of both what CUDA is and how GPUs work, and that will really help you understand as you write your Cocos code or your Raja code or your AMRX code or whatever, like what is actually happening. And I think even just being able to write a set val kernel like this one is way further than you would have been if you didn't take time to think about it. And in particular, you should be able to read a Cocos parallel for loop and then imagine the many parallel threads that are being spawned by this thing on the GPU. It should just be automatic. And maybe I'm biased because I spent like 5 years learning to think that way, and I don't expect you all to do it immediately, but I'm urging you to think with more of that lens. Okay, this was just me being cranky, so I won't do that one. No, I won't do that. Okay, so not all of you are going to work for a hardware vendor, but I hope that you take some time to skill yourself up in how supercomputers really work. I also hope that you take some time to think about non-academic careers. I think it's great if many of you or all of you want to go into academia, but I think that I learned that I could do really cool HPC work and be something like a scientist, like an academic scientist even, working for a vendor. And I think that you can find that kind of job if it's the one you want outside of academia or the national labs. But I recognize you have conflicting goals because you want to do your science and you also want to defend and get jobs and do whatever else grad students do. I'm sure there's nothing else than that. Sorry, I know that all of you are grad students and postdocs, but for those of you who are, I think that it is important as in your early career to stay current with how new technologies work and not accept for yourself the description of GPUs that you will get if you just watch like an introductory talk on how Frontier works. Because that will teach you kind of the top level things like how many terabytes per second the memory bandwidth is and how many flops it has. And you will not really be that much closer to understanding what actually happens when you compile your code. So I think it's really worth taking the time to profile your code, think about what's happening in your code, find the places where things are not doing what you expect, and understanding how to even answer the question of what should I expect in this profile, and then going from there. So I apologize for this extremely random set of observations. I hope some of it was useful. I was going to say something about machine learning, but I won't. But then it will not make this make any sense. But I don't know. I was thinking about machine learning, and I asked it for grad student use as a GPU to do science. And there's like so many things wrong with this. And I apologize for like the lack of women in this. Like it's just, but anyway, yeah. Okay, I'm done. Any questions? Yes.
I'm curious what you have to say about machine learning now.
Thank you for giving the opportunity to do my slide. I'm just going to say, I think that modern large-scale deep learning that people use to do like today's large language models is basically HPC. Like it's scarily like HPC. There's basic things that people, well, not basic, but there's like things that people are solving that are very familiar to someone who's done HPC, like how to distribute work across multiple GPUs, how to overlap computation with communication, how to do an all-reduce operation. They don't always use the same language that we do, but people at Baidu were inventing all-reduce like 30 years after we had done it, and very proud of themselves for it. So like, I don't mean that, I shouldn't be negative about that. I think today, arguably, the frontier of HPC is happening not here, but at Microsoft and Google. And it's worth knowing that because it means that you should be open to the possibility that if you really like the computational science side of what you're doing, not just the domain science, that like a lot of the coolest work is happening outside of the labs. In many ways, the labs and universities are downstream of where the advances in HPC are. So I don't want to say too much more about that except that like there's really cool computational problems happening in modern deep learning today, and you should consider that a valid career path for you if you A, like doing computational science, and B, also like making money. Any other questions? Yes?
So how much easier would you have said it's gotten to program GPUs like after like, I think, because I want to say like before the Kepler series, it was like super difficult, at least all the stuff that I read. But now with like the Pascal and later ones, it seems like CUDA is a lot more simple. how do you feel like it's evolved the past like 10 years in terms of its difficulty?
The short answer is it's a heck of a lot easier, but it's the conflation of two separate events. One is genuinely the tooling for compilers and the community infrastructure just got a lot better. We have Cocos now, which was just in its infancy 10 years ago. We have OpenMP Target. I'm going to be honest, I don't really like OpenMP Target, but it's there. We have OpenACC. It's much more advanced than it was. We have the compilers are much better. But I think the other thing that has happened is that the GPUs have genuinely gotten easier to work with since NVIDIA Kepler. They have a lot more local memory. They have bigger caches, much bigger caches. Like that's the biggest factor by far. It's just less painful to write the code that you want to write. So I think it was a combination of the GPUs getting better at general purpose computing and the tooling infrastructure getting better. But I absolutely believe it's just a lot easier to use. It's maybe even too easy to use GPUs today. Like that's part of the criticism, not criticism, that's an observation I'm making, that it's so easy for you to write code that will compile and run on Frontier or Summit today that you don't even have to think about, in many cases, what's going on. And that is a weird situation compared to when I was doing this 10 years ago, where like, it felt very alien, and it doesn't have to feel alien to you. And I think that that's a wonderful thing, and you should take advantage of that. Yes?
So like, my question relates to like descriptive versus prescriptive parallelism, and like dividing software.
I already answered that. I told you I don't like OpenMP.
Yeah, I mean, so you definitely like gave the point of like you understanding the hardware as you like writing software.
Yeah.
But like, and thinking that same question, just like our hardware, NVIDIA's hardware will evolve many times over the years, and maybe even a new hardware generation that's going to come out. What is like your opinion on like say like longevity of software and encouraging scientists to say write like descriptive parallelism or something that like allows more freedom to the compiler rather than like you doing a lot of things yourself, being more aware of like the inner workings of the hardware you're working with at whatever generation cycle you're at?
I plan my life like a week ahead at most. I don't know how to answer that question. Slightly more serious answer, no, this is still a jokey answer, but slightly more serious, is we get paid to make code better, right? Like, longevity matters because there's some rework is dumb, and you don't want to do it because, like, you could have easily made decisions in the past that would prevent you from doing rework. But I kind of don't think that doing code rewrites is a problem, because these are the opportunities that you get to reevaluate decisions you made in the past that may have actually either been wrong at the time, but you never had an incentive to look at it, or it just doesn't fit the architecture. So I actually don't think that longevity is a particularly good goal for this reason, because the hardware of 10 years from now will be different enough from the hardware today that even if it still runs, you may want the excuse to rewrite your code to adapt to what has changed. I know that's not like maybe the answer people want to hear. At least a lot of people don't want to hear that answer, but that's my take on it. I am not advocating for how you should feel about it. Just personally, as someone who really likes and has fun writing code, like I don't mind doing code rewrites every once in a while. That said, to try to answer your question more directly, I think we are the trend. It is hard to give any prediction from what's going to happen 10 years from now without looking like an idiot, but it seems hard to like escape the basic trend where we are approaching, nanometer-sized features on chips and angstrom-sized features in the next decade, and that will mean that like the problems that we're facing are not going to get easier. Is I think what I currently think is true. That 10 years from now, memory is still going to probably be a problem in terms of bandwidth. We're not going to have that many local memory per thread, so writing for GPUs, because it requires you to be simpler and use less of the language and less of what you can do, actually somewhat I'm going to stop talking because I don't think any prediction I make will be useful. I think that, look, Cocos is good, or things like Cocos are good. Just use that and solve the problems of 10 years from now if you're still in your group 10 years from now. Sorry, I don't know if that's satisfying. Yeah.
So every time I end up trying to re-Google, like, what's the difference between a CPU and a GPU, most of the answers talk about, like, what runs well on a CPU and what runs well on a GPU. Can you give a like short synopsis on the actual like architectural differences that make it that way?
Can I give a short version of that? The snappy line that we would always use when I did training presentations was a CPU is a latency reducing architecture and a GPU is a latency hiding architecture, which means that fundamentally CPUs have complex instruction sets whose job is designed to minimize the time it takes to do any one particular thing. And the way that it typically minimizes the time to do a particular operation requires like clever tricks, like guessing ahead of time what kinds of operations you might be doing, pre-calculating those things, and then inserting that result if it predicted correctly. Doing operations out of order, things like that. GPUs don't do any of that. GPUs basically add numbers together and they multiply those numbers together. And like that's the limit of what GPUs do. So the time it takes to do any one operation is really long on a GPU. And the way that it compensates for that is by having lots of threads. And if any one thread is stalled waiting for this long operation to complete, another thread swoops in, takes its place, and then does its thing. So because GPUs have fundamentally limited instruction sets, the only things they're good at are parallel math problems. Like it's really that simple. And that doesn't mean that CPUs are bad at parallel math problems. It just means like this is what GPUs are good at. It's much easier to say what the only thing that GPUs are good at is large parallel math problems because that's true. And a slightly more nuanced take I would give on that is like there are some kinds of algorithms that don't really map particularly well to a GPU architecture, particularly things involving random memory access patterns where like you cannot group accesses from consecutive threads and together. So like Monte Carlo particle algorithms are like this. They are not super well mapped to the architecture, and you will struggle compared to like a structured mesh code. But if you have a big enough parallel problem, it's going to run fine on a GPU. And the biggest determination of whether you use a GPU successfully is like, do you have at least hundreds of thousands of degrees of freedom to parallelize over? If you do, you're probably going to be fine. If you don't, run a bigger problem.
Cases where there are no, where we have random memory access, how does implementation of one of those programming models, such as Cocos, compared to the USPARS libraries?
Oh, no, that's a dangerous question. Because you will get very different answers if you ask the KuSparse people from if you ask the Cocos people. So I'm going to bow out of that one and say everyone's great at their job. Not going there. Except to say that, honestly, genuinely, both are fine. You will see, the nice thing about that particular part of the community is that everyone knows each other, right? Like the people who do sparse linear algebra in NVIDIA know the people who write the Cocos kernels stuff, and they know the people at AMD. Like it's a very small community, and like, yeah. They know each other. They read each other's papers. Many of them review each other's papers at supercomputing. Like everybody knows about what's going on, and it's not long before an advance done by one group it gets picked up by another group if it genuinely makes things faster. So I think amortized over the long run, it really doesn't matter what you pick because this community really does learn from each other.